Okay, welcome you all to the research talk by Dr. Raghu Ganesh. It's a pleasure to have Dr. Ganesh here. He's visiting us colleaguely from King Abdullah University of Science and Technology in Saudi Arabia. Dr. Ganesh obtained his PhD from Iowa State University and for working on heterogeneous catalysis. He worked on a spin-off company from Jawaharlal Nehru Center for Advanced Scientific Research. The company name is Breathe Applied Sciences Private Limited, as an associate scientist. And for last couple of years, he has been at the King Abdullah University of Science and Technology, KAUST, as a postdoctoral fellow and working mainly on projects which are funded by the Aramco, which is one of the largest hydrocarbon companies in the world. Dr. Ganesh, the floor is yours.
Thank you. So today, most of my talk is just going to be about my PhD work. I'll devote a chunk of my presentation to my PhD work and then transition to what I've been doing in both Breathe Applied Sciences and JNCSR and in KAUST. So the first part of my talk is mostly my PhD work. Like I made these intermetallic compounds, and they were demonstrated for heterogeneous catalysis. Because most of our audience is like, maybe you're not very familiar with catalysis, I'll just give a brief introduction about what catalysis is and why it's important to us. Okay. So catalysis is basically, when you use a catalyst, most processes, they have an activation energy. Like if you want a reaction to go forward, you need to introduce heat, you need to introduce some kind of pressure or some other parameters to make it go forward, like make sure the molecules react and some kinetically interactions happen so that you can get your products, right? So what a catalyst does is that this activation energy part, which is the barrier you have to overcome for your reaction to happen, the catalyst reduces it. So there are two types of catalysis. Actually three. You have homogeneous catalysis, heterogeneous catalysis, and you have enzymatic catalysis. Enzymatic catalysis, people sometimes they say it's homogeneous, sometimes they say it's heterogeneous. They don't really, it depends on the context. You can do, like if you immobilize an enzyme, you can make it heterogeneous. If it's going to happen normally as it happens in our body, it's homogeneous catalysis. So all these three, homogeneous, heterogeneous, or enzymatic catalysis, mostly all they do is they bring down the energy barrier for the reaction to move forward. Okay. So why is this useful? Like how do we use this in our day-to-day lives? Until the early 20th century, many of the processes required very, rough methods of making a particular gas or product which is industrially required. Then you had the Haber process where you had like nitrogen, converting nitrogen into ammonia, right? And nowadays, like ever since the catalytic converter has been the three-way catalytic converter in most of your cars, it takes care of NOx gases so that we don't get poisoned. So all these are catalytic processes where you decompose these harmful gases using some heat. Like normally, if you wanted to eliminate that NOx, you would require very high temperatures. But when you use a catalyst, you reduce the amount of energy required to enact this. And then even in your microwaves, then all your products that you're looking at, methanol, ethanol, anything that you're using in the laboratory is made through some catalytic process. So this helps us bring down the energy costs a lot, and it's ongoing. The development in catalysts to make these processes much more smoother is ongoing. There are many, like right now, CCUS and hydrogen economy are the big things, right? Actually, carbon dioxide is a big problem, and you want to make sure that you can convert it into value-added products. It's there in the atmosphere. There's too much of it there. So you want to be able to capture it and convert it into something so that it doesn't. You can get two benefits. One is reduce the carbon dioxide in the atmosphere, and then get some valuable output. Okay. So I'm just going to basically give some brief examples of what homogeneous catalysis is and heterogeneous catalysis, because my talk is going to be entirely on heterogeneous catalysis because I work on heterogeneous catalysis. So in your in your homogeneous catalyst, you're mostly having processes where all of the ingredients, like your catalyst, your reactant, are the same phase. For example, in this first case, you have ethanol and you have concentrated sulfuric acid. Both are liquids. It's a very fast reaction. It happens almost immediately, and you can get your products. Same with this process where you hydrogenate olefins using the Wilkinson's catalyst. All of these are in the liquid phase. Okay. And it's the homogeneous catalyst has been, even nowadays, if you see most organic chemistry, like pharmaceutical industry and all this, many of these processes, they use complexes like this, which are in the same phase, and you're basically doing like atomic efficiency, like you're making sure that every reactant gets to interact with one atom of the thing to get your product. And it's very efficient. It's very high turnover rates. You get a lot of product, and you can get this thing to work very well. But the problem is you cannot separate this easily from your product. Your catalyst, it's very cumbersome. Like it's in the same phase, right? You have to do some evaporation. You don't know if the compound is going to decompose under those separation techniques and all this. So the drawback is mainly the expensive separation steps. So heterogeneous catalysis, it overcomes this. What it does is you have a solid phase. Your catalyst is usually a solid material, and you have your liquids or your gas coming and interacting. For example, in this case, you have hydrogen coming and absorbing on the surface of the catalyst, and then you have ethene, which you want to make. This is a very simple process. Like this is a Rani nickel. It's very well known for hydrogenation, many hydrogenation reactions, right? So nickel, platinum, all these compounds, mainly transition metals, are very good at hydrogenating any hydrocarbons or other compounds. So the advantage here is, so for example, this is a gas phase reaction, right? My gases come, they embed on the surface of the catalyst, they react, and then they go back out. They leave under the conditions that I'm operating in my reaction. My catalyst stays there as it is. I don't need to worry about separating it from the products. Similarly, for liquid phase heterogeneous catalysts, like you can put these catalysts. Sometimes we will make them as magnetic catalysts. So what you can do is you can have the reaction undergo, but then what happens is after the reaction is done, you can magnetically separate the catalyst, and your product is clean. It has none of the metals. Okay. So the disadvantage of this is, now if you look at this particular process, you have all the catalysts in the molecular form. So the ability to make more of the product or the catalyst to be more effective is higher in homogeneous catalysis. Whereas here, I'm using nanoparticles, or I'm using bulk metals, where the atoms on the surface are the only ones that are actually interacting with my my reactants. But still, this is preferred these days because of the cost. When you scale this process up to a very large scale, heterogeneous catalysis is preferred because you don't have to worry about the expense of separating these. So nowadays, most research is about how you can make it more atomic efficient, like make very small single atoms on a support. You can use an inert support, like say aluminum oxide or magnesium oxide, and you can make atomic, like very small clusters of metal atoms. The nanoparticle gets to be as small as possible. So that's an ongoing field. I haven't done that. So I'll just talk about nanoparticles, which I use for that. So some basic stuff. Okay, in most of the historically catalysis, when they did it, they used monometallic catalysts like platinum or nickel. And the problem with these metal atoms is they don't give you selectivity. If you have a process, if you have a reaction where you have multiple products forming, right? If you use only a particular type of metal, you're not going to be able to control the products you want. This is also a problem, and even for homogeneous catalysis, they have to design the complex in such a way that you can get selectivity to a desired product, right? So what has been the more recent trend is that we mix metals together. We alloy the metals together, either as nanoparticles or as bulk metals. And what it does is it isolates the metal that is active. One of the metals may be inactive, one may be active. The one that's isolated, the way your compounds, the substrate, is reacting with these composites, right? It's restricted. So you forced it to form only one particular product by changing the surface chemistry of how you do it. So most of my talk, I'll be talking about these bimetallic or multimetallic compounds, and some of them will have some amount of ordering, like this intermetallic compound. What happens here is this final compound is completely different from the parent metal atoms. The way the crystal structure, the way it's ordered. So again, you can change the site of a particular metal atom in that crystal structure, and then you can force the catalytic process to go a certain way. Okay. So yeah, so there are many methods to do this. So we do like bulk annealing is what solid state chemists do. They just put everything into a tantalum tube or a silica tube, and they seal it and they heat it at like 1000 degrees, 2000 degrees to get these intermetallic compounds. Those are bulk. So after you get those, you have the problem of you have to take it out, you have to grind it, and then only you can use it as a catalyst powder. So there's a disadvantage for this because most of your surface, the surface is only 1% of your active metal atom is on the surface. Most of it is the bulk. It's not even interacting with your substrate molecules. Okay. So supported annealing. This is mostly what catalysis in industry does. What they do is they use a common support like cheap support like aluminum oxide or chromium oxide, which is not active. It's just a material on which you put your active component. And you put like the metal loading, the loading of your amount of the active component is like maximum 1 to 5%. So this way you ensure that it forms nanoparticles, it's relatively well dispersed, and you have something better than this, where you have more surface. Right? This is what my PhD work was about, so I'll be focusing entirely on this. Colloidal co-reduction is where this is again only you can only use for limited amounts of processes, like main liquid phase reactions where the temperature is relatively low, like below 150 degrees Celsius. And because as you increase the temperature, these things will aggregate and form bigger particles and you lose the surface. So here what I did was I used encapsulation methods like silica encapsulation or metal organic framework encapsulation. And then we would keep these nanoparticles stable inside this, and we could also go to very high temperature. We had no restriction in the kind of reactions we could do. So yeah, so there are many. I'm not going to go too deeply into this. These are papers that we've. So like basically, here these are all using solvothermal methods. We use liquid solvents, like we use some solvents, and we put the metal salts inside, and we heat it like maximum say around 400 degrees Celsius. And we can form nanoparticles based on how these metal atoms interact with each other. Like, specific compositions. For example, I used to work with platinum tin. So 1:1 ratio of platinum and tin will form a particular crystal structure, and that has a particular catalytic activity. So, but then you can also form an platinum 3 tin, which is an alloy, which is a mixture. Like it could be intermetallic, it could be an alloy, and it has a different activity compared to just platinum alone. Okay, so there are many approaches to this. So basically, if you get an ordered compound, what has most recently been shown that these ordered compounds, specific classes of ordered compounds, are very active. I mean, very selective. They may not be very active, but they're more selective to a particular process. Okay, so in my group, what we did was we would make these nanoparticles of platinum first, and then you would coat it with a shell of silica, which is porous. It is porous so that you can have gas and liquid reactants coming through the pores and interacting with the metal atom at the center. Okay. So then we would add another metal and we would form these alloys. We can make these, it's all within the shell. The shell is acting as a nanoreactor where you form these metal nanoparticles and then you use it for the catalysis. There is some issue of the mass transfer, but then we use it to our advantage where if we increase this silica shell, more recently, my group they used to publish papers using these silica shells, only the silica shell, and platinum atoms to break down plastic. You can break down plastic to get useful chemicals. So this length of the shell and the mass transfer acts as an advantage rather than a disadvantage in these kind of scenarios. Right? So we also use metal organic frameworks, but these are expensive because finally the yield of your metal organic framework, and sometimes you're using zirconium. Most of the metal organic frameworks these days use zirconium, and some of them use aluminum and other compounds. But these are very good at controlling your size. You can get very small nanoclusters of these metals. So basically, you have a very highly dispersed catalyst, and you have these pores for the liquids and the gases to interact very easily. Right? So we can use these also as supports, and then silica, conventionally, silica also is good. So for me, I used to make these platinum-based nanoparticles and then make them as platinum tin. This metal could be either tin, lead, or even zinc. And we could use them for various reactions, right? So you can see these are stable at least until 800 degrees Celsius. So I have this porous silica shell, and inside I have my metal nanoparticle, the intermetallic nanoparticle, which is platinum and tin. There is another. This is one route. So this is around each of these core nanoparticles are around 20 nanometers. But we can make it smaller. This is around 4 nanometers. Okay, and each of them have different. So when you have a bulk metal, if the melting point of the bulk metal is going to be around 1000 degrees at a particular for the particular combination of metals, when you make it nanoparticles based on the size, its melting point is going to change. So, but this silica shell provides sufficient thermal stability so that none of these during the reaction they don't colloid, they don't become larger particles, and they can be good catalysts. So yeah, so this is starting with this platinum, and then when you add the tin and you grow it on the tin under those solvothermal conditions, right? You grow it and then you make this platinum 3 tin in this case. Then you have platinum. All the scale bars are the same, but when you add more tin, the tin will selectively reduce only on the surface of the platinum and form this larger particle. And the shell, the silica shell, acts as the reactor to grow these things. Right? So this is the model reaction. This reaction can also be done by copper, but we just use this reaction to show. There are other reactions we tried it for. So these platinum tin intermetallic, we use platinum and we use platinum tin, right? And even we use platinum 3 tin. This is a very simple reaction. You start with furfurylaldehyde, and you want to only get this product, which is furfuryl alcohol, right? You only want to hydrogenate this bond, right? You don't want to, this particular compound on platinum or nickel, it can be fully hydrogenated. All the bonds can be hydrogenated very easily if you use just nickel or platinum. It's just going to absorb flat on the surface of the platinum or the nickel nanoparticle. And all the bonds that are possible to be hydrogenated will be hydrogenated in the present function. But if we make this platinum thin, we restrict the mode of absorption of this particular molecule on the surface of the catalyst, right? So we want only this. We don't want these other compounds. We can get these other compounds to other catalysts if we want to. But for now, for the purpose of my work, I'm going to tell you that we only want to make this, right? So this is platinum tin. Where I use only platinum tin, I get only this product. Okay. Whereas when I'm using platinum, my selectivity to this product is only around 36 to 37%. Okay. And the conversion is also low. So in the case of platinum, I'm getting this, I'm getting this, I'm getting this, I'm getting this. And I'm even getting compounds that are completely broken down, like linear chain compounds. Okay. So you cannot control on the surface of platinum. Whereas just by introducing tin, I have selectively I'm getting only this product. Okay, and even when I reduce the amount, like if I like using 1/10 the quantity of platinum, I can get the same activity as just platinum. So again, I'm enhancing the the usage of my precious metal. Okay. So and the selectivity still remains around almost 100%. I only get this product. I don't get these other products. So from the DFT studies, what we realize is that in the case of platinum, this part is only platinum. These two are platinum 1 on 1, and then platinum 1 on 0. So in platinum, what happens is when the molecule is coming to interact on the surface of platinum, it absorbs flat. You know. So when it absorbs flat, all the bonds that are available for hydrogenation are available for hydrogenation. So it just randomly hydrogenates everything, and you don't get what you want. You get some of this, you get some of that, you get some of everything. Whereas in this case, you're forcing the absorption only through this bond. And this bond is forcibly absorbed only on the tin atoms. Like it's not absorbing on platinum at all, right? So when you force only this bond to atom, on only this bond to absorb on the tin atom, the hydrogen can still come and absorb on the platinum. So the hydrogen dissociates into atomic hydrogen, and then it attacks this bond, and then you form the alcohol. So basically, these intermetallic compounds, most of these bimetallic compounds in industry, what they do is this is what they do. They try to isolate the active component, they try to reduce its activity, and also change the absorption of the molecules on it to enhance selectivity to a particular product.
What kind of interactions those bonds you saw PT111?
Yeah.
What kind of interactions those are? Those are like.
It's just absorbing on the surface of the platinum. Like it's a weak, weak chemisorption kind of thing. It's like this.
Oh,
it's not temporary. It's not
okay, not correct. Okay, the picture it looks like.
Yeah, it looks It's actually just a weak chemisorption, and then like if you are applying some heat, it will go away. Yeah, after it reacts, it will.
Okay.
So how did you confirm experimentally that this is the process that happens?
This is where I'm going to give a clarification. It's DFT, right? They always do it after we give the experimental results to them. So the thing is, see one problem with this particular DFT calculation, they told us that the hydrogen chemisorption will be very high even on this. But when I did it experimentally, I got no hydrogen chemisorption. So in this case, it happens. It happens because otherwise this will not form the alcohol product. But when I measure it chemically, when I did experimentally, when I do the chemisorption, when I try to put the hydrogen and try to see how much of it is absorbing on the surface, because I want to know, right, how much platinum is on the surface. I was not able to get any chemisorption using hydrogen. So DFT, I think we have to give them the data first. So what I did for this particular reaction was I did the kinetics. I got the activation energy, I got everything, and then I gave them that data, and then they predicted this is what's happening. So it's like it comes after the fact, even though it should come before and should tell me how to do my experiment. But in my work, at least, it always comes after I do the experiment.
So the affinity for hydrogen absorption was done with the pure hydrogen.
Yeah.
And how well that will translate to hydrogen associated with the molecule.
No. As in, like normally, no, I didn't get you.
So you are measuring whether the tungsten and platinum both will get hydrogen lax on. Right?
Yeah.
That experiment you did by sending hydrogen.
Yeah.
I'm asking like, no, this hydrogen is not a free hydrogen.
No, this is also free. Like what we do is we put the catalyst in the reactor, and then we pass the hydrogen over it.
No, in this molecule, the hydrogen that.
Oh, here I'm not showing the hydrogen here, but it's mostly only this molecule. But the assumption is that, you know, when the hydrogen comes, it has to go on the platinum. The hydrogen will adsorb only on platinum. So the experiment where I did to confirm the chemisoption, right? Chemisoption is just to know how much platinum is on the surface. So because we couldn't do it through hydrogen, we did it through CO, carbon monoxide. So when you do carbon monoxide adsorption on those, because hydrogen is not showing me any value. When I did it through carbon monoxide, for this particular platinum, it's around 14 nanometers. So amount of surface platinum is around 8%. But for this catalyst, the amount of surface platinum is only 1.2%. So we used a probe molecule to find out how much surface platinum is there. So this reflects in the activity also. When you finally do the activity, this is more active for other processes. It's highly, like, it converts all of it, but you won't get control over selectivity. You won't get to what you want. But in this case, you can control the selectivity. If you can, the reactivity will be lower, but you get exactly what you want. So that's the only thing. So, but yeah, this, like I want to say, and this is a disclaimer that DFT, in most papers, when you see DFT, it usually comes after people have done the experiment. Then they tell you, okay, they rationalize it.
It should not be the case. See, if let's say your experiment is correct and you did not do any mistakes,
Yeah.
and if DFT is not predicting the correct result, then there is some fault in modeling. But
I think it's going to take some time for modeling to come to that level. And it's still on. I think nowadays there's more and more, because they're getting data from us, they're making libraries and getting it to predict, right? So it will take some time. But I'm just right now, what I've seen in most papers, the DFT always comes at the end to rationalize what you've already seen in the experiment.
see, I write paper DFT. There is no experimental part. Just I use DFT and publish a paper. There is no experimental thing there. So it is not. It is not in.
Most of the component, I don't know, I might be wrong in here, what you just said. Many of the molecules that I have seen and I use PFP and PFP, they are basically these strong carbon, hydrogen, oxygen, nitrogen.
Yeah.
Which can very nicely model.
Yeah.
He is looking at platinum, high Z element.
Yeah.
And that is always going to be a problem if you want to model it, because you have to not only look at the normal quantum mechanics, the relative effect also come into play over there.
That's
Where all this has been taken into account in these characteristics, that is an issue.
yeah.
But even then, there is always some maintenance the moment you go to the high Z. So I think that is where they're grappling with the problem, not knowing how to model.
Yeah, and platinum and tin, I would expect very similar kind of, but it is very interesting how for platinum it goes and it sticks flat, and for platinum tin it is like some tilted. And but
No, the valence behavior of these elements are quite different.
quite different.
Yeah, tin, for example, shows to an amount of 4. Whereas the platinum part,
So I haven't shown the data, but the band structure, everything changes when you add this. So
so essentially what you're doing is you're diluting the platinum,
Yes.
reduce its reactivity,
Yes.
therefore enhance the
exactly. That's the best way to put it. Yeah, what you said is like perfectly summing up what I've been doing so far.
but just to answer that why DFT comes in the end, that so an experimental
This is
group,
for
they
my-
do I'm telling you, they do
One thing,
conduct experiment.
one
You
thing. I think if we have DFT, somebody else did it.
Yeah.
Right? The question is what level of theory did they use and what wavelength function did they use?
that is
All that is
that is now I just why it comes in the end, because as experimentalist group you seek help, like, or you want to support your whatever result, then you want to collaborate with some person. That's why it comes like later. But the ideal thing is that you don't give all the data. You should tell that you predict whatever DFT tells, and I will see if it is matching or not. Why you
I
have
just
to
give the
give
data
them that what is the final thing you want? So it is like collaboration from your side also,
Correct.
that you are like insinuating that can you give me this result? Otherwise you don't give any result to DFT people and ask them that you protect whatever you want to protect. And anyway, sorry.
No, but even if we give them some data, right? See, this is like if we had to try and get the mechanism by ourselves, we'll never do it. We won't be able to do it. So when we gave them the kinetic energy data and everything and told them, okay, what's happening there? How is it? They came up with all this.
Yeah.
So it's a reasonable explanation for what is happening.
For that for pyro and Z atoms for basis functions, are as finely tuned, especially in the context of alloy simulation system. That is almost, I think that is why most of like theoretical work's been done to improve quantum mechanical simulation. Carbon, hydrogen, all biologically relevant, but they are trying to figure out pretty well for transition.
The first two period for the periodic table, I think were okay. Then when you get to the further period from the periodic table, yeah, you change your bases, you change your level of theory, so using a different, let's say, use M6 or something, you might get different, and then you choose whichever.
Yeah. You see this in protein simulations also, where when you have, say, zinc ions or calcium or like some ionic metals. What NMR tells you in terms of how the protein structure will be and how the folding alpha fold is different, but in how you take a quantum mechanical simulation. It'll be a hybrid one because proteins will be.
Yeah.
The structure may not necessarily corroborate with the ion. So that ion introduces some level of complexity that I guess modeling hasn't reached to capture perfectly. I think I know this is probably.
Yeah, I don't want to talk, maybe if you continue. At the end of the talk, can you give an example that even with carbon, hydrogen, oxygen compounds, two different levels of theory, we have two different results.
Yeah.
This choice of the crystal, the plane,
Yeah.
111 and 110, is that by design or is that what?
No, they decided that was the lowest energy at which it was happening, and they decided to take that. Again, because there are other, it's not just 110 on which the reaction is happening, it's also there are other places.
So experimentally,
Anywhere it can happen, yeah. Yeah. So then, like, see, we wanted to see that this is done, this particular study. What we did was, so this particular reaction is very important, right? So in the industry, plastic industries and all these other things, you make polyethylene. You want to get from here, you want to use this as your starting material to make polyethylene, right? But sometimes from the natural gas feed, whatever you have this as a poison. This acetylene is there as a poison, and it's not good for the catalyst at the stage where you want to do it. Terminates the polymerization reaction. Okay. So you want to make sure that when you're feeding the gas to your polyethylene process, you don't want this present even in minute quantities. So our catalyst, what we did was we tried to show that, okay, listen, again, this here too, the adsorption behavior of this and this is completely different on our intermetallic compounds compared to just platinum. If you use platinum, it's going to just fully hydrogenate from ethane. You're not going to be able to control the hydrogenation, right? So in this case, what we did was we used our platinum, and what we noticed was in the platinum tin, there's very low amounts of ethane forming. Almost all of this is being converted to ethylene, because again, the forced adsorption, you can only form a weak interaction of this on the diluted platinum surface, right? And then you get only this, and so you get almost 100% selectivity to forming the ethylene, and then you can go to the next step of polymerization, right? So again, these intermetallic compounds, basically, it's making sure you isolate the most active component and then try to push it towards selectivity. Now, here, most of the reactions I've shown are very simple, but there are applications where you can divert the selectivity to a completely different product. So then we tried this other reaction where you have this nitrostyrene, and we use the same explanation that we use for the alcohol, again, the mode of adsorption. And we could selectively get, this compound. Using the platinum 10, you could only get this green compound. You can see for platinum 10. For platinum 310, you would get a mixture of this and this. In the case of platinum, we only got this, the fully hydrogen compound. So that's what platinum does. It just gives you the whole. Yeah, but one disadvantage is the turnover rates on these intermetallic compounds is slightly lower, but that's, I think if you're looking at selectivity more, this is the more valuable prospect. Then we also could control the like cis trans isomerism. You can control if you want to get only the cis isomer on these platinum 10 compound, we could do just by controlling how hydrogen adsorbs on this particular, how the hydrogen reacts with this thing on the catalyst surface. Like the hydrogen interacts from only one side and forces it to form only that particular isomer. Like you're getting only the cis side. On the case of platinum, it's just going to, you're going to get the fully over hydrogenated product. So yeah, this is my work in my PhD, and like basically, if you see the theme here, mostly I work with precious metals, which is not feasible for large scale. But I cannot use platinum and palladium wherever I do. So I tried to incorporate some amount of copper and other metal things, but I couldn't do it. By the time I finished my PhD, it was mostly palladium and platinum. But when I came to KAUST, when I came to first to breathe applied sciences and then to KAUST, I was only working on non-precious metals like copper, zinc, and then nickel, cobalt. Cobalt is also slightly expensive, but when you alloy it with other metals, it's starting to make sense. So in this particular part of my talk, I'm just going to talk about my work that was done in KAUST and mostly funded by Saudi Aramco. Yeah.
I had a question actually a more fundamental question.
Yeah.
When we talk about diluting this platinum with tin, are there sort of discrete steps of dilution that when I say dilution, right?
Yeah.
I'm assuming it's pretending that it in the sense that what I saw glimpse of when you're shown the slide, the order in which the molecules place themselves.
Oh, this one? No.
Okay, it was.
Synthesis itself, right?
I think just before this one, but basically, yeah, this.
Yeah.
So the order that is created, that sort of, like, if I'm thinking in terms of how closely compacted the purple atoms are together, that's it. How much control do you have in terms of how far you can guess possible?
So it depends on, so basically if you, most of these solvothermal synthetic methods, right, they're very, you don't need to have very great kinetic control, or you don't need to be very careful like how you do an organic reaction, organic synthesis, when you use a particular reagent in this. But here stoichiometry matters more. Like if you use platinum and tin in an equal molar ratio, it will form the most stable intermetallic compound. If I use it in the ratio like 3:1, it will form that intermetallic. So there are some phase diagrams for these compounds. If you look at those and use those ratios, right? And for this reaction, what I realize is just even if I just use a high temperature, like it forms at a particular temperature, but even if I use a high temperature, it doesn't matter. After the thermodynamics takes over, it will form only that amount if I put that ratio. So in some cases, what we had to do was, if I want to dilute it more or less, sometimes I have to form one compound first. Let's say I form platinum 3 tin, or like in the case of palladium, I used to make these palladium 2 tin compounds. If I want to make a different, more thermodynamically difficult compound, I have to make this compound first, and then I have to do it in the subsequent step. Yeah, it's like, but I cannot do it straight away. It's not a direct way to do it. So, but these reactions are not very complex. It's only that I had to do some initial trial and error around what temperature, the initial temperature that is required. But then it's very easy to make once you decide what compound they are. And they mostly facilitate very straightforward catalytic processes.
And also on this, like, as we change derivation, what are the catalytic characteristics that you find in terms of, let's say, we have a more dispersed platinum. So
I'll show you. I think that's a good question. I'll show you a good example. So in this case, right? So here you can see that this on this particular catalyst, right? And this is platinum 3 tin. It's not as diluted as this case. On this platinum 3 tin surface, I'm still getting ethane. I'm not getting selectivity, right? It's as active as platinum for this particular reaction. And then for platinum 10, I'm not getting any ethane. So in this case, there's still some platinum atoms together. If one platinum atom has access to another one, they're like contiguous, they end up overheading. I don't get what I want. So based on how, and I've just shown you bimetallic systems. There are people who are doing trimetallic systems and multimetallic alloys, and they're using like high entropy alloys now. So when you use more and more metals, you can change the selectivity to different products too. So the problem with heterogeneous catalysis is not as effective as homogeneous catalysis yet in terms of the wide variety of reactions you can try. With homogeneous catalysis, it's more, you can control it, right? You know exactly what your complex is. You know the kind of ligands that are around it, and you can control the selectivity. We have not achieved that yet with this extent, but it's on the way. Because heterogeneous catalysis is always preferred. You want to separate your catalyst from industrial process.
What is the advantage of this encapsulation?
So the encapsulation, for example, this reaction, right, is happening at 200 degrees. Then we use this for propane dehydrogenation also. That is happening at 650 degrees. So at 650 degrees, I want to make sure my particles retain the integrity. They don't congeal and become bigger particles. When it becomes bigger, then my activity drops.
Okay.
So if it aggregates, it's gone, and I cannot. Right.
Yeah.
So this particular catalyst.
Yeah.
Yeah. So for this particular catalyst, so they use this for plastic disproportionation also. The silica shell itself is a reactant here, where as a catalyst here, where it breaks down the plastic into smaller fragments that we use as value-added fuel. So they go up to 400 degrees and like 30 bar, high pressure, high temperature, and these particles will retain their type. They will not. So the activities we can use it for a long time, like almost like 2-3 months continuously.
Yeah.
So the stability of the catalyst, the encapsulation provides that. So now I'm just going to talk about some more. So most of my work right now is more industrially oriented, like the relevance of CO2 utilization and how what we did at both breathe and in Kaust. So this particular thing, right? I've been even in my teaching talk, I was talking about CO2 hydrogenation. If you look at this process, it's reasonably exothermic, but then you're using 3 moles of hydrogen, and then an equilibrium gets established after some time. So even the best catalysts that we use for this process you don't get to convert more than like 30 to 40% of the CO2. Like you're using 50 bar, using high pressures, and you're using this around 252. Like if you see here, the CO2 feed, right? You're not getting much of the methanol. The methanol yield decreases when you go to a higher temperature because you end up making this reaction happen instead of this, right? So because this is more, it's an endothermic process and it's favored more at higher temperature. And sometimes it forms methane also. So in the case of your CO2 hydrogenation, the maximum yield you get of methanol is around 40%. And in this time, the conversion is not that good. Like at 200, it's at 250 degrees that the conversion is ideal, right? But if you see in the case of carbon monoxide, if you want to get methane from carbon monoxide, you can get more of it at just 200 degrees Celsius, more exothermic, and you can easily convert all of the carbon monoxide to methanol. So in my project, first working in breathe applied sciences, we used to do this process, which is not very efficient. But when I went to Kaust, we moved to another process called DRM, dry reforming of methane. So it's an indirect way of hydrogenating this to methanol. So what happens here? So here, this is a highly endothermic process, but you get syngas, highly reactive carbon monoxide and highly reactive hydrogen. Okay. So here we use this magnesium oxide support, which is made in a different fashion. And this is a nickel molybdenum nanoparticle, right? So under reaction conditions, before we start using the catalyst, we first treat it with the reaction gas. So in this particular case, the nickel molybdenum nanoparticles, it goes to certain defect edge sites on this magnesium oxide. Okay, it goes there and stabilizes at that surface. And this nickel molybdenum nanoparticle, it efficiently converts the CH4 and CO2 into carbon monoxide and hydrogen. Okay, you avoid these reactions. There are other reactions which take place, but like some coking. Normally in this DRM, dry reforming of methane, coking happens. What happens is when you give very high temperature to CH4, it forms carbon. But in this case, because we were using this magnesium oxide support and the synergy between this nickel molybdenum and the magnesium oxide, it was burning away the coke and giving us more of this carbon monoxide. We're getting only this as the product. Even the backward reaction, this reaction taking place that much. Not this reaction, but it's not efficient. So we are mostly getting carbon monoxide and hydrogen. And so this is a more efficient way of converting your CO2, and the conversion at equilibrium is almost, like you get 98% conversion of the CO2 and 98% conversion of the methane also. At 800 degrees Celsius, that's the equilibrium. Okay, almost completely converts. And then we can use this to form alcohols, hydrocarbons, anything like Fischer-Tropsch is a very common process. All plastics, everything you make, many of the polymers, everything are done through CO and hydrogen is the starting material. So yeah, so my project later, and I have not put any data because I'm still in the process of processing it for paper and everything. But so what we did is, so this is the first project I was involved in, where we make this NinoCat. It's called nickel molybdenum on magnesium oxide. We convert this dual greenhouse gas mixture into these value-added products like carbon monoxide and hydrogen. And then the process is to convert this to ethanol. So this is pretty easy because rather than using CO2, if I use just this mixture of syngas, like carbon monoxide and hydrogen, I can get ethanol very easily. So it almost like from the most recent catalyst I was working, I was getting almost like 80% conversion of this mixture, a very stable catalyst. I'm just using copper, cobalt, and aluminum, and I can make the catalyst overnight, like large scales. So this is the more viable method of doing CO2 utilization. Like you can convert it first indirectly to this using DRM, and then using this you can convert it to this. So this is being explored by Aramco for a larger scale. So I don't know, it's continuing in my old group in class. So another project we use that same magnesium oxide support for ammonia synthesis, right? We realized that our magnesium oxide support is slightly different from the commercially available magnesium oxide support. So I put cobalt molybdenum on it and we nitrated it using ammonia. We formed this cobalt molybdenum nitrate, which is kind of an intermetallic compound. It's a very ordered compound. And it's been known for the last 20-25 years for the conversion of activation of nitrogen to ammonia. So cobalt molybdenum nitrate, before this paper, mostly we make the bulk catalyst. You just put everything, put the salts inside, add some ammonium hydroxide, and then you form the precipitate. And then you heat it at like 800, calcine it and then reduce it. But you have a bulk catalyst, you don't have nanoparticles. Here, using this magnesium oxide support, we can get this very well dispersed cobalt molybdenum nitrate on the MgO. And when we tested it for ammonia synthesis, so we made two catalysts. A control catalyst. Usually, when you do these kind of experiments, you make a control catalyst and you make your actual catalyst, right? So this SaMgO is the sigma aldrich. You can just buy it from sigma. It's an MgO, a nanoparticle powders, like it's around 50 nanometers each MgO. But as we went higher, the pressure, right, like some 10 bar, 20 bar, 30 bar, 40 bar, we noticed there was almost a 4-fold increase in our catalyst, in our supported catalyst compared to the, and this catalyst is even more active than the bulk, which is obvious. So here what we realize is because this cobalt molybdenum nitrate interacts with the magnesium oxide and forms a more basic catalyst. Surface of the catalyst is more basic. So we measure this basicity using CO2 adsorption. And that's why for this particular process, you need to have a more basic surface for it to be facilitated. Especially the molybdenum acts as a very good site for the nitrogen to split into individual nitrogen atoms. Otherwise, it's very difficult activation. So then we also tried photothermal ammonia synthesis. In this case, we used a xenon lamp, right? And here we can reduce the pressure. We can get the same activity. Here I have to use 50 bar to get 10 millimole of ammonia, whereas in this case, using photothermal ammonia synthesis, uses xenon lamp and only 10 bar of pressure and lower temperature also, and we can get almost a similar amount of ammonia synthesis. So this basically what I'm trying to say, right? If you want to increase, you cannot just ignore the value of a support. If some of these supports, they're as active as the catalyst itself. They can, through some synergy, you can make sure that you get better catalytic activity. Yeah, so my plan is basically, now that I've come back to India, I'm going to try to continue to work with Professor Sebastian. So he has all the resources, he has the reactors, the resources, the characterization techniques also in CNCSR. So continue this, but because they are still exploring CO2 hydrogenation, I want to introduce DRM as a method of indirectly converting the CO2 into syngas and then getting ethanol or other value-added products. So the other option is also like, CO2, more recent papers, they've shown that because of this equilibrium limitation, if you add some additional reactant like plastic, polyethylene, terephthalate, right? You can keep on pushing the equilibrium to form more and more methanol. Because the moment the methanol is formed, it's consumed to form something else. So then I keep on shifting the equilibrium towards the right by consuming the methanol at the moment it's formed. So this is also something that can be explored if you want to stick with CO2 hydrogenation. So yeah, so these are some my plans. I don't know how far I can execute them while I'm here in India, but this is my hope to do it. Yeah, that's my talk today. You guys have any questions?
Yeah. I have a question about so using the CO2 for we have catalysts or any materials that can efficiently capture CO2 like atmospheres.
Yeah, so there are many materials. So there's a professor called Professor Omar Yagi. He does a lot of this work, but this is a problem. Right? It's scaling up. When you scale up these materials, the chemical engineer comes into the picture. That we have no expertise. What happens is huge amounts of heat are released when you absorb. Absorption processes at small scales, even my catalysis, right? When I was doing a small glass tube, milligram quantities of scale, I don't notice any heat changes, nothing. My sensor is only measuring the heat I supply. When I came to breathe, you were working with 1 kg of catalyst, right? In a huge reactor, which needs 6 people to load the catalyst inside. It has six temperature sensors. So we started the hydrogenation, we started flowing hydrogen, 15,000 ml per minute. So it's a lot of hydrogen, right? On a copper catalyst. At 150 degrees Celsius, my temperature that I was supplying was only 150 degrees. The temperature shot up to 400 degrees. So the same thing happens with your carbon capture, CO2 capture, right? So if you make a material, like mostly it's metal organic frameworks or covalent organic frameworks. Most of these materials that the stability is like 200 or 300 degrees Celsius. Beyond that, they degrade. The crystal structure completely collapses. So when you scale it up and you're absorbing large quantities for industrial process to make it feasible as a wide scale application, you have to account for the fact that absorption doesn't release so much heat as to destroy your carbon capture material. That's a common problem for CO2 capture. There has been one, it's called CALF 20, that is successfully been done in Canada or somewhere else. CALF 20 or CALF 20. So that one doesn't. But there are not been, like, it's not yet gone on the scale. It's being explored everywhere else. But mostly people now, they're only using potassium hydroxide, converting it to K2CO3 and then heating it to release it back. But the energy of that, like, it's a carbon positive process so far. So just basically doing like large watts of potassium hydroxide, putting CO2 inside, forming potassium carbonate. So only the engineers have been able to devise the process. Moment someone gives them a material that can withstand all these heat changes on a large scale, then it's true.
If the budget is not a constraint, so what kind of laboratory will be needed to characterize situations?
So mainly what I used to use is I need mostly we use chemistry instrument. Okay. That does like the basic test of the surface much. So a powder XRD machine for sure. Okay. Transmission electron microscopy, that doesn't make sense because only really big institutions here in India have it, like ISC and maintaining it. But mostly a chemistry option instrument, then powder XRD. All the other things you already have, like the IR. Like we used to use an instrument called a drifts. It's an IR instrument, but you can in situ monitor a reaction, some simple reaction to characterize the surface. But I don't think
we don't have drift, we have ATR.
Yeah.
But drift can always be
upgraded.
That's not.
So drifts we basically use. So that's how I mostly characterize my using carbon monoxide or CO2 or nitrogen as the core molecule, just to understand the surface, like what kind of changes happen and. So, but mainly the chemistry option instrument is the most thing.
So how much is the price of the approximately? But is it like crores or?
No, it's not crores. It's like a very basic setup.
But powder XRD, I think that is kind of very expensive or no?
No, but we can get a simple one, right?
Still may quote.
Yeah. No, but the one that's like a tabletop, it's like
Tabletop you can get for 50 lakhs.
Yeah.
56 tabletop. For the XRD, you have both powder XRD as well as single crystal. Tabletop machines are
the single crystal one will be more expensive for sure.
not terribly more.
So in the last slide, did you show that in your future plans, if the baked plastic that is broken down by
Yeah, CO2, like we can just do it with this is one paper I saw it. Because the thing is this looks interesting because you have a problem, equilibrium, and you're trying to overcome it by adding another reagent, another thing. So this is I only saw one paper on this. Okay, but when I saw it, I thought, okay, this is something I need to explore. If I'm going to be limited by the kind of reactor I have. For example, this is done in a high pressure vessel. It's not in a flow mode. So high pressure vessel, if you can, some of the processes they use like large high pressure vessels and they can do this. So you're solving multiple problems here. You're taking care of plastic waste and you're taking care of CO2. So in that sense, like this, if I get that particular, those are not very costly. The one that we bought in jeans was around 6 lakhs. So 300 ml high pressure vessel.
Like it was worth it. And one, similar question I asked is that you have to your methanol, carbon dioxide, and nitrogen.
Yeah.
That's your problem. And carbon, I know methanol is soluble in water, therefore, but it's not used to thing. We not use, things like molecular sieves or not. They don't make for methanol, and they don't let the.
Yes.
And they are that pretty.
I think some people do that, but like they do use molecular sieves too. Like, pull out the product,
yes,
and then force the equilibrium to keep on coming to the side.
And because removing the stuff from the molecular sieve later has a lot of big deal,
But again, right, it's a question of scale. When you increase it, it becomes a problem. Whereas here, we just keep adding the PET, something that's waste. You don't even care about it, you want to get rid of it, you're forming something else useful. That's just thinking, right? This is something that's. So, like in Professor Sebastian's lab, they do electrocatalysis also, and they do photocatalysis also. So, those are.
More philosophical questions. I've always had a problem with organic chemists telling me that they use palladium catalysis and platinum catalysis and all this. Many of which, like the Suzuki reaction. The problem with it is these are elements that are going to be extinct very soon.
Yeah.
I always keep joking that when Mendeleev discovered the periodic table, he only knew the physics elements for the others that we know. And very soon we will get back to the state where most of the elements in the periodic table will be available for us. So that means how sustainable are these methods that we come from? Process we develop with the palladium, platinum, and all these materials, the rare materials. I'm talking about the long, like the next 100, 200, 300 years.
Yeah.
Are these the reactions? Of course, there might be different technologies with that thing. But are these sustainable for such long?
What I know for a fact is that most of these palladium and platinum can be replaced with something simple, like with nickel, copper, which is more abundantly available. But people don't do it because they've scaled up their process to such an extent that they don't want to change the catalyst for 6 or 7 years.
But you'll be forced to.
They'll be forced to eventually, yes. But they will do it only at that point. So I'll give you an example from my Aramco work. They funded us for 4 years. It started with when my professor was in Korea. It came to the stage where we sent it to a company, an industrial testing facility in Germany, and they tested the catalyst was reasonably good. But Aramco said, okay, we're stopping this now, let's move on to something else. Give a new proposal. Because they didn't want to continue with it, because they already have an established catalyst. And they don't want to change out these catalysts as frequently as. For them, it's so you have to make a cost, apart from the science that we do, we have to make a commercial case to these people that say that this is what's happening. If you don't do this, you're going to lose money.
You're not willing to look at the commercial aspect of it, which is like 100 years.
Yeah. Yeah.
Some plastic recycling processes that are very sensitive, extremely sensitive to impurities.
Yes.
Especially like patterns and PVC. Patterns of chlorine that came from EDC and they're hoping for recovering that spot.
Yeah.
So how sensitive is the entire reaction be through impurities? We move on to, let's say, a scalable thing where you're digesting plastic at an industrial design. How pure would that have to be, and what are the implications of it? What does it take to make it pure enough so it doesn't, mess up the equilibrium when you're trying to conserve?
Yeah, so the thing is, that's a very good question. So now the thing is, most people what they try to do now is that chlorine is a big problem. All these, especially all these catalysts. So what they try to do is try to make catalysts that are resistant to chlorine poisoning. So either that is one option, or you have to do what you said. You have to purify and remove all chlorine, completely get the chlorine out. That adds a cost aspect to your. So yeah, because even most of these, even this CO2, like for example, when we were doing this carbon express competition, right? They were telling us to go and use flue gas. When you use flue gas, you have other impurities. You have H2S, you have sulfur dioxide, you have sulfur dioxide. Those will poison your catalyst. So the most convenient way to do this, even for TRM, if you want to use direct flue gas, you have to make a catalyst that is resistant to those poisons, ppm level poisons, which will not kill your catalyst. So some of the work we did here was like for the demo cat, we tried to add some other metals like tungsten to prevent these other gases, these ppm level poisons from poisoning the catalyst. It has to keep on happening.
So just another final question that, unless there's no question that. So when you were trying to find this metal combinations that alloys and then included in this thing, is it eventually possible to come up with a framework, like a theoretical framework that from which one can predict it already? If I'm trying to do these combinations here and look at. Or is it entirely trial and error? Or
I did trial and error, but there are many papers that show which is the best combination. There are many good papers. Now they're building like so. They're building a library of these alloy compounds which are good for this. Like when you make this combination of metals, for example, Intermetallic, which is better for HER, which is better for OR, that you can get the ideal combination. For example, in this particular cobalt monazite, right? It's the theoretically and it's experimentally proved that they are the best combination to do both nitrogen and hydrogen absorption, so that you can form ammonia. So there are a lot of papers. But for my PhD work, I did trial and error. But
I think some sense there's a question about when you vary or when you should be how does it affect sort of things that and we construct these frameworks as that we
it's being done as we speak. I think people are doing a lot of theoreticians are trying to find the ideal so that we can help the experiment. Otherwise, we're wasting time in trial and error.
Theoretic can be done before experiment also.
No, it's like, and some of those, see, the problem with theory, every time you see in publishing, right, theoreticians and experimentalists always have a fight. Like I've seen too many papers where they send the letters to the editor and they don't even hold back the criticism of, telling the theoretician that what you're saying is wrong. I proved experimentally. So until that balance comes, it's going to be.
I was telling you about an example. You are looking at a very simple organic compound. The ester of phosphate and the trimethyl phosphate. And calculations done in the mid-80s, where all the methods are not so developed. When your computing power was not as strong.
Slater type of orbitals.
HF was the best, even molecular classes for motivation. So there was a experimental work done on the same molecule that we were doing experiments for. And they had shown that this molecule has two configurations. And let's say that B is more stable than A. That is their prediction. We did the experiment, and our experiment clearly showed that A was more stable than B. And all we did was that let's redo the calculation, what they had done. That was right. But we upped the level from 44, we went to from what 321G to 631G. 631G said that what our was right. Experiment which was in keeping with the experiment. And then you did the MP2. MP2 also observed that A was more stable than B, and that's what the experiment showed. But their earlier work clearly showed that was the other way. So actually, we sent it for publication. One of the referees asked, okay, at that level of theory, B is more stable. The other level of theory, A is more stable. Then if you go to still higher level of theory, again, if it says B is more stable, then how are you going to handle it? So we have no problem. Experiment says A is more stable than, so we only take that theory, which can be produced, and then use that theory for all other predictions. So I think that is, today we won't have the problem. Today, because nobody will use it as to do it. You will use FP2 or you will use GFT and so on. Then it's perfectly fine. But I think when it comes to metals and high Z numbers, we are at the position we were there in 85 for carbon hydrogen compounds. we are there today for the platinum compound. So maybe with the theory further develops on this, we'll have more meaningful predictive capability.
No, but there are already some papers like for many of these based on already existing data. They've compiled trends and other things. And so they're trying to-
So I'm guessing the algorithm is that if the theory matches the experiment published, if it doesn't match, go to the higher level of theory, if it matches it, then published.
But another thing, the theory matches the experiment published. If it doesn't match the experiment, still published.
Yeah, you get the citation wrong. You get the wrong kind of citation, but you still get the citation.
Yeah.
I just ignore the theory and after it is in collaborator, you send a sorry note that.
No, you publish. When those meetings you go to higher level of theory and then say my earlier work was wrong, then this we wanted.
No, don't say it's wrong. That approximation is not adequate.
Yeah.
It's criteria.
Yeah.
I do not know about DFT. I think in the original Pond's paper, there was a bound on energy that you can protect. On that work for high excitation. When they do in nuclear physics, they do very similar, many body problem. But then also it was an independent function. They have quite strong bounds on the system. So their calculations are a bit more reliable. On cross section, only energy, their calculation.
And DFT also this exchange correlation part, which is like fitted parameters, so you never know it can. Yeah.
That's why the bounds become important. It's whatever strength you put in. The solution is going to be bounded between these two.
Okay.
Somebody can give a tighter bound. That sorts your bound. Let's say, suppose I claim it will light, whatever you do to light in 1.1 dB and 1.3. That, but if I say the volume of this 1.2 dB, then you entire universe for
Yeah.
No, I'm just checking in case the online audience, if there is any question, but
Go on.
no, actually no one. So that's what the other part of the question. So.
That's another one, Leo.
Okay, then thank you all. Thank you, Dr. Ganesh, for this wonderful talk.